Hello, good evening. I'm really honored to give this keynote address at the International Workshop on the Opportunities and Challenges for the Internet of Things at Sastra University in India. And I'm Dr. Bhavani. I'm the Founders Chair Professor at the University of Texas, Dallas, and also the founding executive director of the Cybersecurity Research and Education Institute from 2004 to 2021. And I also co-direct the Women in Cybersecurity and Women in Data Science Centers. So I would like to first share my screen. Yes. And also I'd like to point out that this is a recorded presentation. So our time is February 2nd. It's around 7 o'clock in the evening, United States Central Standard Time. And so I always make a recorded, almost always make a recorded presentation in case there is a technology glitch, because I'll be giving this presentation in around 2 hours from now live. But I do so that's going to be February 3rd at 9 o'clock in the morning, Indian Standard Time. Okay, so the title of my talk, Integrating Cybersecurity and Machine Learning / Data Science / AI, Artificial Intelligence, with applications in Internet of Things. And in particular, I'll be talking about one aspect of Internet of Things, which is Internet of Transportation Systems. Okay, so my talk is going to be in multiple parts. The part one is integrating cybersecurity and AI / data science / machine learning. In particular, I'll talk about big data security and privacy, privacy aware quantified self, data science ML AI for cybersecurity applications, securing data science ML AI techniques, and trustworthy machine learning AI. So these are various topics, and each topic we've done some work, some more so than the others. Part two is going to be security and privacy for Internet of Things. In particular, I'm going to focus on Internet of Transportation and Infrastructures. Remember, when we talk about Internet of Things, it could be Internet of Transportation Systems, Internet of Home things like your cell phone, your smartphone connected to your computer, connected to your microwave, connected to your refrigerator, connected to your television, right? And there's also Internet of Healthcare things, your pacemaker connected to various other gadgets. And similarly, Internet of Transportation, the cars connected to the trains and so on. And then I'm going to integrate part 1 and 2, applications of AI in smart world systems, Internet of Transportation and infrastructures. Okay, so first part, integrating cybersecurity and AI, data science, machine learning. Okay, so some motivation. So I believe I introduced this topic, data mining, security, and privacy. I gave a keynote address at the IFIP 1996 Data and Application Security and Privacy Conference. And that was around almost 26 years ago, this July. And I later gave a keynote address at the Pacific Asia Knowledge Discovery and Data Science Conference in 1998. And that was in Melbourne, Australia. And I call it a landmark paper because I was a program director at NSF at that time, National Science Foundation, in 2002. Because when you're a program director and when you publish a paper, then everyone actually quotes that paper, right? Because you're responsible for giving funding. And then, of course, when you stop being an NSF program director, hardly anyone quotes your paper, unless, of course, it's a very good paper. But still, this paper had a lot of citations. Okay, so then IBM Almaden, Dr. Rakesh Agarwal, he came up with this highly original idea, he and his colleagues, about privacy preserving data mining. So the whole idea is that you have the original data, you add some noise to the data, and because, see, you don't want to tell your age or your salary, so instead of saying you are 25, you say you are 26, and it's not going to make that much of a difference. Instead of saying, but if you're 25 and if you say 75, of course, the results could be skewed, right? So 25 to 26, or your salary is 30,000 and you say it's 35,000, right? So you add noise and you get X prime, and then you have the modified data mining process, and then you have the final modified result. So Then when I joined the university in fall 1994 with a top expert in privacy preserving data mining, Dr. Murad Kantarjalu, we had a joint student, Dr. Li Liu. Her focus was on privacy preserving decision trees and perturbation. How do you perturb the data? So since then, there's a lot of work. IBM folks came up with privacy preserving association rule mining, then privacy preserving decision trees, and privacy preserving neural networks, and so on. So data mining, security, and privacy, it's been exacerbated with big data and data science. And so we hosted the NSF workshop on this topic, big data security and privacy, in September 2014. And we presented the results to various interagency working group in February 2015. And so big data management, security, and privacy. So what did we do? Because of technological advances, right? Lots of applications, we can now capture, process, analyze large amounts of data for security tasks. Such tasks include user authentication, access control, anomaly detection. So a lot of the security tasks, we need to collect data, because when you want to authenticate, if you have, say, multi-factor authentication, not just your password and so on, your fingerprinting, your handwriting, and your voice. And so a lot of personal information is being collected. And for non-cybersecurity applications like healthcare and finance, right, lots and lots of personal data collected. And so if you put that data and integrate it with known data on the web, right, you could have, really a bad situation because your privacy could be violated. Although this data analytics is really important for disease outbreaks, homeland protection, like for COVID-19, it was really very, very helpful. This collected data, even if we anonymize, right, we can remove identifiers, but when you link the data together, you could re-identify, right? You've got two records, right? You have no identification, but when you link these records together, you can identify the person. So as I said earlier, security tasks like authentication, access control, right? They require detailed information, multi-factor authentication. This information, if misused or stolen, can lead to privacy breaches. And the directions include securing the data, access control models, privacy enhanced techniques, big data analytics for cybersecurity. And so what I'm going to focus on, big data for cybersecurity and securing machine learning. What's the point in applying AI and ML for everything if your machine learning techniques are attacked? And then I'm also going to focus on privacy. Okay, so first we'll talk about privacy. We had a joint project we wrote a paper with Purdue University. Mobile devices like smartphones have become prevalent computing platform, and there are billions of users. And the recent emergence of quantified self movement, right? What do we mean by quantified self? That is, social scientists and psychologists are saying, wouldn't it be great if you can collect all the information about us, right? And do targeted therapies. Because if they have, there are a lot of companies that are being sort of started on providing therapeutics based on cognitive behavioral therapy. So you collect lots of information about people, you analyze, and based on their behavioral patterns and so on, you target them and you provide therapies for diseases like heart disease and diabetes and so on, right? And so without a doubt, it's a lot of help for humans. But by collecting data, right, you can have a disastrous situation because privacy could be violated. And data could be shared with others. And again, a lot of benefits, but collected data sharing, right, carried out without the user's knowledge could be grave danger. So glucose device monitoring, right, data collected by device monitoring glucose levels, insurance company could deny coverage, not just to me, say if I've got high glucose, it could deny coverage to me, to my son, and to my grandchildren. And that could be disaster. Oh, your grandmother had a high glucose, so the chances are you're going to get diabetes, because they find that diabetes is somewhat genetic as well, right? It has a genetic predisposition too. That's what scientists are saying. Okay, such privacy violations could easily get out of control if data collectors could aggregate financial, health-related data, Facebook activity, and so on. And then, it can bring lawsuits and it causes physical distress. So because of these growing challenges, we need tools. And so what are we doing? So these are the gadgets, right, that we are using, glucose monitoring and so on, and the Fitbits. Okay, so what we've come up with, privacy aware quantified self, a data management framework. what we are saying, okay, so essentially what we are saying is health data, fitness data, location, social media, and so on, all of the data is being collected. Data collection, data storage, data analytics, data sharing. Some of the data is going to be encrypted and stored in the cloud, and through cloud-based services, you can have access to the data. And this is what we have developed, Privacy Aware Quantified Self-Manager. But what we are saying is policies have to govern every step of the way. I can't go and just start collecting data. So policy-aware data collection, policy-aware data storage, policy-aware data analytics, policy-aware data sharing. And that's what we have come up with. This is our mobile device, cloud-based storage. So policies have to govern. Now, who develops these policies? Remember, we are computer scientists. And so we develop essentially like TOY policies, right? So as more data are collected, the storage on the device will not be sufficient to store all of the data. So we envision an encrypted cloud storage component where all the data and or less frequently access data are pushed to the cloud. Okay. Based on the access control policies, right, local applications running on the device, right, will be allowed access to some of the encrypted data stored in the cloud via a simple query interface, right? So in some cases, you may not need to collect all the data. When you are 20 years old, the chances are you can say you eat a lot of food and the next day, okay, so you put 3-4 pounds. So what when you are 20 and when you don't have any pre-existing conditions, right? But when you are 70, you might also have some pre-existing conditions, you overeat and you feel full, and that could really damage. Your blood pressure could shoot and go up, your blood sugar could go up. So it's a disaster. So you need to weigh yourself every day. Whereas when you're 20, you don't need to weigh yourself. So because you don't want to collect lots of data. I mean, you want to collect, but not unnecessary data, right? Because there's only so much storage. In other cases, the data may have to be deleted to preserve privacy, right? But then how do we know when the data is deleted? Do we know these people are really deleting the data? It's not like going to the bank and putting your jewelry and then taking your jewelry out. That means we know that the jewelry is no longer in the bank. But with data, you don't know. So you need to audit to make sure that the service provider has indeed deleted the data. We envision that data sharing and analytics will be carried out using services running in the cloud. So based on different scenarios, some of the data could be sent without modifications, heart rate, and so on, and some randomized, perturbation and so on. So anyway, so the whole idea, what I'm trying to stress is that policies have to govern. We are computer scientists, so we have to work with policy experts, top policy experts. So we work with our policy expert, Dr. Jennifer Holmes. She's our dean of the policy school. And so we work with her to come up with some realistic policies. Okay, so now I'm going to talk about data science for cybersecurity applications. So essentially, and I'll talk in a minute, this is joint work with my colleague, Professor Latifa Khan. You use past data to build classification models, right? And predicts the labels of future instances using the model and helps the decision-making process, right? Great. Now, just looking at that, this is something I could have said 25 years ago. I first got started in applying what I call data mining for intrusion detection. And we build past data for classification model, predict the label, and help with the decision-making process. But what's the difference? At that time, right, we did not know how to do real-time machine learning or real-time data mining or whatever, right? So we build a model and we use that one model. But one size does not fit all, because why? Data is now so much of data, and data is arriving in streams like healthcare data, financial data, like stock market data, what else? Cybersecurity data, right? They're arriving in streams, and the concepts may be different. Today they say by Microsoft, tomorrow by Apple, the next day by Google, next day by Amazon, and what else is left there, right? So every day, or Facebook, every day you're buying different stocks, right? Because things are changing. So that change has to be captured. So concepts are changing, and also infinite length. So what we do is we get all of the data in chunks. We develop a classification model, right? And this model is changing. As the data changes, we redo. So if it's, let's say if it's benign traffic, we let it go through. If we find, again, it's model building, right? Training and testing. If it's not benign, then we then we block and quarantine. But this model is changing, so periodically we change and the model is updated. That is the challenge, because we've got big data, massive data streams, and continuous flow of data. And so that's the challenge. Concepts are changing. That's called concept drift. Great. Now we apply to a lot of various applications. In particular, a sponsor at that time, about 10 years ago, was very particular that we develop a system for insider threat. Again, insider threat detection requires identification rare anomalies, because bad people could be pretending to be good people. It could be people who are carrying espionage, or in our case here, the bad processes, malicious processes, pretending to be good processes. Okay, so we have designed and developed ensemble-based, I'm going to talk in the next chart, right? Stream mining or stream machine learning algorithms. And a number of things, our typical go-to algorithms, we always use support vector machine. We also do a lot of neural networks and decision trees. But it can be applied to any of these machine learning algorithms. So we have also designed supervised, like support vector machine, unsupervised. When we have no labels, then of course, how do we guess the labels? We might have to use machine learning to guess the labels. So there is some work on that as well. In unsupervised learning, compression-based techniques are used to model common behavior sequences. This results in a classification exhibition, a substantial increase in classification accuracy. And that was a bit surprising that unsupervised performed well. Okay, so what is our model? So what the person is typing away, and then we look at all of the patterns typing. So we look at, remember, streams of data coming in. So we look at I chunks, right? And then we train feature extract. How do we train? Feature extraction. And then, okay, the I chunk, right, comes here. We extract features and our learning algorithms, unsupervised and supervised, right? And we develop an ensemble of models, collection of models. Models could be like M1, M2, M3, M4, and so on. Somewhere down the road, maybe M3 is invalid. It's bad. It's outdated. So the models have to talk to each other. We have an automated algorithm where the models talk to each other, and we throw away the bad models. So M3 is gone. And then sometime later, M1 is outdated, right? So that's what we do. And then the I+1 chunk arrives. We extract features and we test, right? Because we have trained the models, ensemble. And then we test, and then we know, is it an anomaly or not? Okay, so now machine learning for cybersecurity. Now, the biggest challenge we are faced with, because now remember, machine learning is going to be used for everything. Now, the biggest thing that we are discussing is this chat GPT. Machine learning algorithms, AI, is generating papers and so on. So we are terribly worried that students could use it to generate term papers and answer questions and whatnot. So it's really going to encourage cheating behavior. And so machine learning is could be used for bad purposes, discrimination and all kinds of stuff, right? Discrimination, machine learning techniques could be attacked. It could discriminate, not give loans to certain individuals, maybe women and underrepresented minority communities. And what else? So, okay, so all these bad things could happen, right? Fairness, bias, discrimination, and so on. So we are focusing on one thing. What happens if these machine learning techniques are attacked? Adversary modifies data to defeat the machine learning algorithms. And we have to understand adversarial learning, right? We have to understand how the adversary is performing. Adversary is trying to learn and thwart about us, thwart our data, thwart our machine learning models. And so we've got to learn what the adversary is doing so that we can thwart the adversary. So it's not concept drift. It's not online learning. The adversary is adapting to avoid being detected. Yes, during training time, data poisoning, during test time, modifying features when data mining is deployed. So it becomes a gameplay. So we and the adversary, we are playing games, right? So let's give an example. So this is the support vector machine boundary line. Everything about the above, red squares, are bad instances. Below, the blue circles are good instances. So the adversary is following what we are doing. and it's trying to thwart, knows that what our model is trying to thwart us. And once it has studied, 1, 2, 3, 4, 5 bad instances are pretending now to be good instances. And so now we say, okay, these are good instances, but then they could do untold damage. So what do? We've got to study what the adversary is up to, and then we've got to some or other react, right? But we have to be more proactive, not always react. So we need to think ahead what the adversary is doing. Okay, so before I talk about what our approach is, I want to explain a little bit, and I don't want to go into the details. The adversarial attack. So our paper was one of the early papers of adversarial machine learning. And we have a free range attack, right, where adversary can move the malicious data anywhere in the domain. And then we have a targeted attack. Adversary can move malicious data closer to the target point. So these attacks, right, I mean, there's a lot of mathematics, because remember, game theory, right, is based on economics and mathematics. So a lot of mathematics in order to really figure out exactly how should we react for each attack. And that's the problem. Adversary has 100 attacks, and we are now trying to find out only 2 classes of attacks. In the real world, there could be many more attacks. But what I'm trying to say is something is better than none. Or some people might say that's going to give us a false sense of security. So, you can decide, right? Something is better than none. And if that's the case, is it going to give us a false sense of security? In any case, a solution for us, remember, the red squares is a bit reversed. The red squares are bad instances. The green circles are good instances. So what's adversarial machine learning? The threat model, what can the attacker do? It can modify the data from X to X prime, like modify packet length, adding dummy bytes, add good word to spam email, add noise to an image, right? So this is our original support vector machine line. These green circles are good instances, and the red crosses are bad instances. So what the attacker is trying to do is to push as many green circles as possible down, many red squares across as much as possible here. So if this is our support vector machine line, original, all of this will be considered to be good when they are really bad, right? So what are we trying to do? The black dash line is what the support vector machine would have given, but we are now studying the adversary's patterns, and we are trying to move the dash line to the blue line. So blue line is the adversarial support vector machine, right? Line classification boundary. So it's going from here to here. By doing that, a lot of these bad instances now are caught, but still some instances are getting away with it, but we have caught quite a bit. So the challenge is, how far do you move this blue line, right? If you move this blue line right here, then you can catch all the bad instances. But guess what happens? All the good instances will be showing as bad instances. So we don't want false positives, and we don't want false negatives, right? So we've got to draw a balance. So in this approach, we will not be able to catch all the bad instances. But again, some bad instances will be caught. And then what I'm trying to say is something is better than nothing, right? If you want an all or nothing, right? If you want all the instances to be caught, I mean, that's going to be much more challenging. So what is research all about? Remember, back in the old days, when I first got into data mining, applying for cybersecurity, our false positive and false negatives rates were like 30%. You were accepting it then, but today it's totally unacceptable. Even 2% is not good these days. We need to come up with an error like 1.0000 something, right? So hopefully when we do more research, we can come up with some good solutions. Okay. Now, another group of people, now I was on a panel with a lady at University of Oxford, and she said, the whole idea is to use formal methods, right? Formal verification methods for machine learning. So some of the things that we have done, not so much informal methods, computations over big data may require massive computational resources, and organizations may use a third-party service to outsource some computations. When a third-party service is used for computation, data becomes available in untrusted environments, right? So what we are saying is, because we are outsourcing so much, so the data has to be Data could be, there could be man-in-the-middle attacks and so on, because all of the analytics is being carried out elsewhere. So what we are trying to do is to, and not just us, quite a few people, try to use Intel XGX, secure encrypted stream data processing, and trustworthy analytics to support trusted execution environments. That's TEE. So that's what we are trying to do it in hardware. And then this lady from a professor from Oxford, she's saying formal methods for machine learning include logic specification for deep learning and the verification of the machine learning algorithms. Okay, so that is trustworthy machine learning. And so that's sort of, okay, so here is our approach using hardware, Intel chips. So what we're essentially trying to do is to execute a lot of the code in the secure locations, right? SGX enclave memory, right? These are secure trusted regions. So executing the data analytics in trusted regions. So that's one solution, doing it in hardware. So forget about all the game theory stuff, just execute them in hardware. And then another approach is formal verification. So a number of approaches, and let's hope that something will work. Okay, so now we finish part one. Let's see, I'm going to part two, security and privacy for Internet of Transportation. And critical infrastructures. Okay, Internet of Things is, as I said, your home computer connected to your smartphone, to your refrigerator, to your television, whatnot. But we're talking about Internet of Transportation, right? So this is your home, Internet of Home Things. Transportation, your cars, talking to each other, talking to trains, talking to roadworks, talking to trucks. And the Internet of Things has major implications in transportation industry, autonomous vehicles, aim at improving day-to-day activities such as delivering packages, improving traffic, transportation of goods, and so on. In the US alone, 63%, 2/3, right, percent of the freight of goods trucks are carrying. AVs are not limited to ground. They could also be aerial, like what? Drones and airplanes, and sea vehicles, submarines and ships, and so on, for a wide range of applications. Levels of automation for AVs range from 0 to 5, with current ground vehicles in the market having partial automation at level 2, and aerial vehicles have high automation at level 4. Companies are investing heavily in AVs. General Motors spent $728 million in R&D. That was in 2008. 18 is an outdated chart. In 2009, yes, they did go to $1 billion, and now in 2020 and beyond, a lot more money. While there's great potential in AVs and the improvements it can do to the transportation industry, security and privacy concerns pose new challenges that need to be addressed as we move forward. Okay, security of autonomous vehicles. AVs, right, they emulate their environment using a variety of sensors, like what could they be? Camera, GPS, inertial measurement units, LiDAR, radar, ultrasonic sensors. Previous research has shown that sensors are susceptible to malicious tampering. And inertial measurement units, IMUs, are susceptible to sound waves. And GPS, global positioning system receptors, are susceptible to spoofing. So various types of attacks for various types of gadgets. So, but what's the challenge? Vehicles, they've got so little memory. So you can't use traditional techniques for computer security for the vehicles, right? AVs relies on sensors to interact with the environment. Sensors are susceptible to GPS spoofing. We said that, right? And manipulate physical signals, visual, sound, magnetic. Classical computing security, memory protection, cryptography, and so on may not work. So we need to come up with special techniques because real-time constraints, right? You can't just, the data is rapidly changing. AVs trust and act upon sensor data without any form of verification. Okay, so we came up with a very small, you might say, okay, what's the big deal here? Physics-based anomaly detector. We use physical properties, right? We computer scientists, we are not really physicists. So I worked with Dr. Cardenas, who is a top-notch cyber physical system, and he's a control engineer by training and a PhD in cyber physical systems. So we built a reference monitor. That's the part of the system that cannot be penetrated, right? So that's reference monitor using a physics-based anomaly detection, PBAD. So algorithm has 3 parts. Build a model offline using all the AV's physical invariants, fine. Implementing an online tool to monitor expected and observed behavior to detect anomalies, great. Raise an alarm if significant residual difference exists between executions. So offline processing, online verification, anomaly detection. So you can say, what's the big deal? right? That's what we have been doing for 25 years. The big deal here is to get the model right. Because once you get the model wrong, right, then it becomes a big challenge. So offline processing, the AV's invariants are calculated using a well-known non-linear model for aerial and ground vehicles. Accelerometer, gyroscope, magnetometer, sensor data on the XY, Z-axis or Z-axis or Z-axis for the aerial vehicle, vehicle position and steering. Okay, so this is the model. So like K state, YK input sensor measurements, right, input, and Y tilde K is pre-processing sensor reading, and UK commands to the roots. Where is U? Okay, UK. X pronounced X hat, the X hat predicts states. LX, LY, LZ or LZ moments of inertia needed for nonlinear equations. M is mass, D is drag vector, applicable to drone, B is thrust vector. So that's our model. Now, online stage, we just use very simple, not machine learning, extended Kalman filter. It's been around for a long time. He's used to predict AV's physical behavior by estimating unknown parameters from noisy sensor inputs. So we divide the algorithm into two sections and predict and corrects the estimation before it is compared against the sensor data. Anomaly detection, CUSUM, statistical algorithm, is then used to detect persistent attacks. An alarm is raised if the residual difference is larger than a predefined threshold. Okay, so we did some very interesting implementations for drones and for cars. We didn't do for ships and so ground vehicles and aerial vehicles. For aerial, we used Intel ready-to-fly drone controller PX4 flight controller focused on detecting GPS spoofing and gyroscope attacks. GPS detected after 0.2 seconds, while gyroscope after 1.5 seconds. And earlier I mentioned what these types of attacks are, right, for GPS and gyroscope. Let's see, overall overhead is 5.4, so that's a little bit too high. Ground, custom built on Traxi Ford Fiesta rally chassis controller ROS kinetic aim, focused on detecting visual attacks on the camera, attacks detected after 0.1 seconds. Overhead introduced 2.2501. Each threshold produces a probability of false alarms of approximately 2%. Okay, so this was 2% is still today's term, it's not good. 20 years ago when I started this kind of research, it was fantastic to get 2% because we were getting, as I said, 20 to 30%. So these are results presented in Newsnext and so some other conference as well, the CCS conference. Okay, so privacy and infrastructure. So beyond the security of individual vehicles, the transportation sector could greatly benefit from a supporting infrastructure that allows communications between vehicles, motion sensors, lamppost surveillance cameras, and so on, to help identify traffic jams, reroute vehicles, increase vehicle safety, right? That's the privacy. Because again, we talked about security, but privacy is important as well. But without a doubt, we need to do machine learning, right? So beyond the security, the transportation sector could greatly benefit from supporting infrastructure, allows communication. So all this communication between vehicles and lampposts and so on. From the user's perspective, with all this communication and analytics going on, there's privacy concerns because I don't want my location to be known. I don't want people to know who I'm visiting, right? So I want my privacy. And then if I know that these technologies are privacy enhanced, then that there is more chance that I will be using these technologies. So legislators, engineers, and scientists should keep privacy concerns in mind as advances in IoT become more prominent in day-to-day activities. This will aid at improving public perception, reduce hesitation from consumers, and increase the adoption rate of new technologies, right? Because then I'll have some confidence that those technologies are being put to good use and privacy is being considered. Okay, so that's something, right? Privacy. We haven't done much, but I'm going to talk a little later. So my last part is very quickly, I'll finish. Applications of security and AI for Internet of Transportation and infrastructures. Okay, so first I'm going to talk about how can we apply machine learning AI for transportation. So we said Internet of Transportation subject to attacks, just like any cyber physical system. Streaming data. Data is streaming because all this communication coming from sensors, autonomous and in the future driverless vehicles as transparent transportation systems go electric, we need energy conservation. Threats to the security of such systems could cause massive damage, including accidents, loss of lives, as well as stranded on lonely highways due to attacks on energy management. Data science, machine learning techniques are being applied to analyze the data. And so the question I have is, can stream analytics, like what we discussed in the earlier chart, remember big data stream analytics, how can we apply? And we have applied it for telecom and financial data. How can we apply it to transportation data? The main question is to understand the nature of this complex transportation data and adapt our algorithms, right, to analyze the massive amounts of data collected. So that's data science, integrating AI with transportation security. Next, adversarial machine learning. So we talked about adversarial machine learning, the machine learning techniques could be attacked, and we just looked at some sort of usual, networking data. Part for Internet of Transportation, that's also going to rely on machine learning. It's going to, without a doubt, machine learning is going to be extremely helpful, right? Because we have to analyze all the communication between the cars and the roads and the roadworks and the trains, and warn the passengers, the train is approaching, so slow down to 20 miles per hour or 20 kilometers per hour, right? Very, very useful. But adversary is going to learn all that and then tell the car, no, you can cross, right? You can cross the rail tracks now, knowing full well the train is arriving. What happens? Crash. So adversary will attempt to thwart our process, and therefore we have to learn about what the adversary is doing and thwart the adversary. Eventually it becomes game playing, and so challenges what sort of game, zero sum, Bayesian, and so on. So there is some work that's being applied, not a lot of work on adversarial machine learning for autonomous vehicles. Okay, so another thing is privacy. Not much has been done on privacy. So what I'm trying to say here, remember, we talked about policy-based, privacy-aware, right? Data management framework for, say, healthcare data, social media data. Instead, can we come up with a privacy-aware, policy-based data framework for IoT? So that for transportation, we collect radar, GPS, cameras, LIDAR, ultrasonic, all of this data is collected. This small gadget, like what's in our smartphones, is in the car. Policy-based data collection, data storage, data analytics, data sharing, and encrypted backup data in the cloud, and some other services being obtained. So we are building essentially a privacy-aware, policy-based autonomous vehicle. We haven't done that, but that's the future, I think. So policies have to govern all the data collection. So when we collect the data, we've got to say we are using it for a specific purpose. After we finish using it, we won't use your data for anything else, and we won't share your data with everyone. Okay. And my last chart, the directions. Developments integrating cybersecurity and AI are exploding. Applications of AI for security, right, inside the threat detection, adversarial machine learning. Also developments in privacy-aware healthcare management, one's life's activities, privacy-aware quantified self. At the same time, with the development of Internet of Things, Internet of Transportation, right? Transportation systems and infrastructure, security, privacy solutions are being developed. As driverless cars become a reality, more and more of the AVs will be used in AI ML techniques. How can we develop AI solutions for detecting malware in AV systems? And how can adversarial machine learning in AV work? Can we develop privacy-aware policy-based data framework for an IoT, Internet of Transportation? And remember, we talked about trustworthy machine learning. Can we put in an Intel chip in there? Trusted execution environment. So that's something we haven't looked at for transportation systems. And then what about formal methods for IoT security, right? So there are numerous opportunities for substantial research. And that finishes my presentation, right? Lots of people to thank for this particular work. Dr. Cardenas, right? He was one of our colleagues at UT Dallas, now he's at UC Santa Cruz. He is cyber physical systems expert. Dr. Murad Kantajalu is an expert in privacy and adversarial machine learning. Dr. Khan is a top expert in machine learning, and he applies machine learning for a number of applications. Dr. Raul Quinones is our PhD student, Dr. Cardenas and my student. He's now working, for in the industry in this area, and Ms. Rhonda Walls is our project coordinator. Now, I'm going to stop sharing. And so I'm going to see you all in about, oh gosh, I don't know why this happens. I'm so sorry. I got to restart, but I don't want to restart. Okay, so, right. So I think, yeah, I see you all at in around about an hour. I think an hour and a half is when my talk starts, and I will join in about 1 hour. And one thing I want to tell you is that, AI is going to be everywhere, right? In the beginning, like 5 years ago, I was a little bit skeptical, but now I'm convinced with all the readings and everything that I'm doing. So I've been working in what's called AI since the 1980s. I was at Honeywell and developed an expert system for process control systems. Expert systems were like, capturing the knowledge of the expert, and then we program the system. So it's like a lot of if-then rules, right? All this, if this, if that, and, lot of rules to identify, so we get the information from the expert and say, if this, then this will be the disease, right? So that's program. So we do programming, but now it's all about learning. From programming, we go to learning. So those expert systems are long gone. At that time, right, we're talking about 35 years ago, right? I did this project in 1986, 87. So actually 35, 36 years ago, it was all about programming, right? And capturing the expert. But now it's about learning. We give lots of examples, right? In this situation, this is what we did. This situation, this is what we did. And so the system is learning and learning and learning. And then when it sees something similar, it's recognizing, right? And so that's the way of the future. So instead of programming, it's all becoming learning. And these learning models could be used and reused and adapted. And I think that's where the future is going. And so something that I'm, as I said, over the last 5, 6 years, and the more and more I'm getting, convinced that the future essentially of computing, to me, it seems to be right now, is in AI, right? So, but remember, with respect to security, any technology that we develop, it can be attacked. So as we use AI and machine learning more and more, the hackers are not going to keep quiet and say, okay, so it's AI, so we just keep quiet. No, they are going to attack, right? And AI is also could be doing some bad things, like this ChatGPT thing that we have been talking about. I mean, in some ways it's good, generating some good papers and so on, for important applications, but students could also use it and cheat. And so we need trackers. Are they using ChatGPT? So there's going to be a lot of work and a lot of opportunities, because AI is going to be there. So we need to make sure AI is doing good things. And we also have to make sure that the AI systems are not attacked, right? So that's sort of the gist of my presentation. And again, thank you very much. And again, this is a placeholder presentation just in case there is a technology glitch. So far, it has never happened. I mean, I've given, after the pandemic, I've given probably about 40, 50 keynote addresses and so on. Only once at the end of my presentation, there was my internet went down, but I have also a backup internet that I can use immediately if there's a problem. And so, but then that was at the end, and then I got back again. So hopefully it'll be okay. I'm going to send this presentation to Dr. Hemavati so that she has it in hand, right? So thank you very much, and I will see you in about 1 hour. Thank you. Bye. Let's see. I'm going to stop recording, stop recording.